Hello everyone, sharing my screen. I hope I am audible. Hello all. So in the last week, you have learned about the microscopic techniques, and before that, and the previous week, you have learned about the spectroscopy techniques. So one of the questions which came after the session was the UPS technique. So some of you wanted to know about the UPS technique, and there was a question in the assignment also related to the same. So I'm going to give a brief idea about the UPS. So basically, XPS and UPS both are photoelectron spectroscopy, and they uses the effect photoelectron effect, which is uh, which is actually nothing but when we are projecting our electromagnetic radiation on the sample or the surface. So then, because of the interaction of the electromagnetic radiation, the electron in the shells are getting ejected from the material. So that can be from the valence, like from the core electron also, or it can be from the valence electron, depending upon which radiation we are using. So in the X-ray photon, we generally use a very high energy radiation because X-rays are very high energy radiations. So in that case, it ejects the core electron basically from our from the shell. So the core electron is getting ejected from here. And in the UV photon, what happens because the energy is very less? So only the valence shell electron will get ejected. So this is the difference, major difference between the XPS and UPS. And so therefore XPS will give us the nature of binding because here the core electron is getting ejected. So that's why it will give the information about the nature of binding. And in the UV photon or UPS, it has very few electron volts of energy. So energy is from around few electron to few tenth of electron volt, not more than that. So it provides the information about the density of states. So that is the major difference between these two. So based on that, the assignment question we can solve now. So the statement one says UPS uses high energy X-rays with photon energies of 200 to 2000 electron volt. And the second statement is UPS focuses on valence electrons. So now that I've explained what is UPS, so can you tell me which one is correct, or either should both of them should be correct, or like neither of them? So can anyone tell me which one is the correct answer? Yeah, exactly. So as I told, the UPS uses does not use the X-rays, but it uses UV photons. So that's why the statement first is wrong, because here it says that UPS uses high energy X-rays. That is wrong, and still again the energies are also very less than 200 basically. So actually it is less than few tenth of the electron volt. So this is also wrong. So therefore, and also it focuses on the valence electron. So statement 2 is the correct one, and 1 is wrong. So therefore, the answer D is the correct answer. So now we will come to this week's module. So in this module, we have learned about the microscopy techniques, the basics of microscopy basically, the like what are the sources and contrast and resolution, these kind of terminologies, and the interaction between the light and matter, and the numerical aperture, dark field, bright field images, and there are some errors called spherical and chromatic aberrations, those you understood in this. So I'm going to give a brief overview of this, and then we'll talk about the optical microscopy, simple and compound microscopy. Just a second. Yeah. So optical microscopy, confocal microscopy, then fluorescence imaging, etc. Then scanning tunneling microscopy, STM and AFM, atomic force microscopy. And if time permits, we'll look at the SCM and TEM basics also. So starting with the microscopy. So microscope actually helps us to view small objects in a at a magnified scale, basically. So we can see very small, tiny objects which are not visible from our naked eye, but we can magnify those objects with the help of a microscope, and we can easily see them. So they come with a wide range of shape and size, and there are various types of sources like light based, electron based, ion based, X-ray based, or even mechanical probe based. So that helps us to produce a signal and to give a image or a micrograph. And microscopy is the technique which is used to view samples and objects that cannot be seen, as I told, with the unaided eye, and it explores the relation between structure and property for a very wide variety of materials, ranging from polymer samples, composites, biomedical samples, or metals, depending upon our application. So, starting with the history, so Yuan Hock was the first to actually uh, able to make a microscope, and he used hand-grown lenses to magnify the object around 200 times. So he is known as the father of microscopy, and he was the first one who demonstrated how a simple microscope uh, can be developed. So he has used very hand-ground lenses, which are, and he again did the observation of bacteria and protozoa, and his research was related to the microbiology. So that was about the history, and then there are few things to consider when we talk about the microscope. So first one is the source, as I told. Then we have contrast, uh, which uh, which is basically to difference between the depth of fields. I'll talk about it also in the next few slides. Then the resolution, magnification, and numerical aperture also takes a very plays a very important role. Then we have bright and dark field images. So starting with the source of radiation. So first is the visible light, and it has a wide range of wavelength, as we know, the Vibgyor. So the different color of light or wavelength of light is they are present in our visible light. Then we have the laser beam, which is a very focused light source. Then we have other electromagnetic radiations other than the visible light, that is IR, UV, X-rays, and we can also use electron beams to focus on our object or sample, and with the help of the electron beam we can as similar to the light one. In the light, in the optical microscope we use lenses, and in the the electron beam microscope we use a magnetic lens. So the difference is only in the lenses to be able to focus the beam. Then the contrast. So yeah, so here, as you can see, the depth of field is different because these are so this is the surface and this is the depth, or what you can say, crease present in the object. So different depth of field plays important role. So here you can see that you can easily see the contrast. Because of the contrast, we can see that there is a depth in the picture, in this object. So that is what makes it understand better. So contrast play a very crucial role in the microscopy. So it is basically a contradiction in luminance or color that makes an object distinguishable. And in visual perception of the real world, contrast is determined by the difference in the color or brightness of the object and other objects within the same field of view. So in the same field of view, we can see that there are some crates present on the surface, and because of the contrast, we are able to actually differentiate these objects. Then we have phase contrast. So phase contrast is basically how we are able to look at the small tiny details present in our picture. So in the left figure, we cannot see the boundaries very clearly, but in the right one, we can see the boundaries are very clearly distinguished. So that is the it is the part which is the phase contrast technique, in which we introduce a phase difference between parts of the light supplied by the condenser, and to enhance the outlines of the sample or the boundaries between parts differing in the optical density. So depending upon the optical density, the parts will look different, like different in the grayscale. Then we have the resolution. So as we know that in our digital cameras also, resolution plays a very high very important role, because the higher the resolution, the better we will be able to see the image, the more clearly we will be able to see the image. So that's why we always try to purchase a high megapixel camera and something like that, so that will give us better resolution uh, as compared to the lesser one. So it basically gives us the more detail about our image. So here the points are very nearby, so the points we are taking is are very close to each other, that's why we are getting a very clear picture. But here, the as you can see, the blocks, those are very far from each other, so that's why we are getting a blurry image. So that is the major difference between the low resolution image and the high resolution image. Then so mm, sorry. So now the sources of the light. So as I told about the sources, so one of the source is the light, uh, the visible light, and we can correlate it with our perception of light. So when we see the light from a very far away source, like from the stars, that will come to us as a plane wave, because it is situated very far to our eyes. So that's why we in our perception, it feels like a plane wave. And if it is in a Gaussian form, that is paraxial wave. So these are again different source, like different propagation. Then if we have a point source, so that will give us a spherical wave. So suppose there is a bulb at the center, and it is producing the light. So that is in a spherical wave form. And if the point source is situated at a very large distance, then it will give us a spherical wave again at a large distance. So the circle's ring will be like uh, the diameter of the ring will be large. So then the modes of light interaction with matter. So as we know that when a ray of light falls on a material or an object, then it can either reflect or refract, or if it is a ray, then it will reflect back. So suppose if it is the surface is very smooth and very shiny, and without any what would you say, roughness, it is very smooth and shiny. In that case, the light will totally reflect back. So and very little absorbance will be there. So reflection of light is the angle of incidence is equals to angle of reflection. That is a normal law which we have probably learned in the school. So that is reflection, and then we have diffraction. That is the bending of light. So because of the bending of light, we are seeing this pencil as a like as a distorted one, but it is not actually distorted. But since we are not able to like since because of the media that is having a higher refractive index, we are assuming it as it is distorted, but actually it is not. So that is the phenomena of refraction. Then waves. So waves can either interfere or diffraction can be happen, or polarization can happen. So in the interference, it can be either constructive or destructive. So what is constructive? In the previous lecture also I told that when the uh, amplitude, sorry, uh, when the high intensity coincide with the other waves high intensity beam. So this theta angle, if it is coinciding, then we are getting a higher amplitude. So this amplitude of these two waves will get sum up to give us a higher amplitude wave, which will give us a constructive interference. And if this is not so if it is not aligned properly, then if it is the minima is intersecting with the maxima of the another wave, in that case we will not we will not get any amplitude, and that is called the destructive interference. So that's why when in the previous one you can see, so at some places the intensity is high, at some places it is less. So this is how the interference happens. So at the high intensity region there is constructive interference, at the low intensity region there is destructive interference. So similarly, you can see here. So in the high amplitude one, we are getting constructive interference, and when it is cancelling each other, in that case we are getting a destructive interference. Then we have diffraction. So as you can see here also, the same thing is happening. So diffraction is the scattering of light from a small uh, aperture. So suppose we have a source here, and the wave is traveling in this direction, and it is passing through a slit, through this slit. And again we have two more slits in this path, so it will try to make this kind of circles. So as you can see, when so where the surface this these two rings are coinciding, on that parts we are getting a interference pattern. So likewise, we are getting constructive interference, then destructive, then constructive, then destructive. Likewise, we are able to see this kind of structure or pattern. So this is called the airy pattern. Then we have polarization. So polarization can be so it is actually to make the wave in a linear or unidirectional form. So we have an unpolarized light, so it has an electric field and magnetic field, and we have then if we put a polarizer in between, it will eliminate the this field, that is the magnetic field. But we are only getting the in a single direction in both the fields. So that is the polarized light, or that is linear. Then the particle nature. So when the light is getting absorbed, so what is happening? The incident light is having a spectrum of all colors, like starting from the violet to the red. And whenever it falls on a object, so suppose if it is falling on a leaf, so the property of leaf is that it will absorb every light except the green light. So that's why we are able to see the green color of the leaf, because that is getting reflected, and it is and our eye is perceiving that color. So that's why we are able to see it as green, but it is not green actually. Why we are seeing it as green? Because we are uh, seeing the reflected light coming from the leaf, because every other light is getting absorbed. Then the scattering. So scattering is the again it is a kind of diffraction only. So suppose we have a source of light very far from our perception. So in that case, the light will be in all directions. It will not come in a single direction. So that is because of the scattering of light. It will scatter in various directions upon hitting a surface. Or suppose there is an object, then the light is falling over here, and then it is after coinciding with this object, it is getting scattered. So likewise, uh, this scattering phenomenon happens. Then there is fluorescence phenomenon. So fluorescence is basically when the electron in the ground state is absorbing some kind of light, suppose UV light or any wavelength of radiation, and it is going to excited state, and then it is getting relaxed back from the same state itself. Then it is called fluorescence. So after relaxing, at the time of relaxing, it will emit some light, and that is how we can see a fluorescent material. So yeah, so suppose we have a fluorescent material. So, as you can see, different colors are visible here. So these can be nanoparticles or quantum dots. It can be any of those, or even the neon lights you can see in the dark. So what happens that it absorbs the light from the visible source, and then it emits the light at a different wavelength. So suppose we are seeing the green color of the object. That is because it is emitting the green light. So that's why we are able to see it as green. So that is the phenomena of fluorescence. So in the absence of light, there won't be any color, but when the absorbance happening, when the light is getting absorbed, and it will emit a certain color. So without, suppose if it is absorbing a UV light, then without the UV source you will see it as transparent or some other light color, but after absorbing the UV light, it will appear as a dark green because it is emitting in that region. So that is the phenomena of fluorescence. Then we have phosphorence phenomena. So phosphorence is when the excited electron from the ground state to the singlet excited state, it jumps to another excited state, that is called triplet excited state. And from there, if it gets relaxed back, then that phenomena is called as phosphorescence. So the only difference between the fluorescence and phosphorescence is that the excited state is getting changed. So in the fluorescence, the excited state is remains the same, but in the phosphorescence, the excited state will change. So that was about the interaction of light with matter. Now, how the image is formed. So suppose so in a plane mirror, uh, what we are seeing is that we have a object here, and uh, we are seeing at the same point. So and this is the mirror. So this is the point of incident. So here the incident ray is falling on it, and it is actually making a virtual image here at this side of the mirror, and we perceive it as if we are inside the mirror, but it is a virtual image. So that is how we are able to see ourselves in the mirror, or any other object in the mirror. So that this is the image formation, how it is happening in a plane mirror. Then we have convex and concave lenses. So in the convex lens, we are actually able to converge the light to focus at the focal point. But in the concave lens, we are actually diverging the light. So this is the basic difference between the convex lens and the concave lens. You might have known it as well. And then there are certain conditions, if so where to put the object to get a real image or a virtual image or inverted or upright image. So that depends upon where we are positioning the object. So in this case, actually we are not changing the lens position but the object position. But in real life, we cannot change the object location, but in real life we have to change the location of the lens to get the desired image. So suppose if I want to diminish the image, so in that case I will put the object at 2f of the distance or more than that. So object or the lens depending upon the application. So in that case, if I'll put the object far from 2f, so in that case I'll get a very small image that is real but inverted. Then if I put it at exactly 2f, then I'll be getting the same size image, but it is real and inverted. Then if I put the object at the focus, in that case I will not get any image, but the reflected rays are very parallel, so that's why they are not converging, so I'm not getting to the image. And if I put the object in between 2f and f, in that case I will get a very large magnified image, and it is real but inverted. And if I put the object in between the focal length, in that case I'll be getting a very large image that is upright but virtual. So depending upon the application, we can put our object, or basically the lens, in the real life conditions. Then in the concave lens, so if I want to get a image that is upright but it is diminished, so in that case I have to put the object far from the focal length, and I'll be getting an image that is in between the focal length of the mirror or the lens. So that is about the lenses. Then another important terminology is the numerical aperture. So numerical aperture of a microscope objective is a measure of its ability to gather light and resolve fine specimens. So actually, the higher the numerical aperture, the higher will be the resolution, or the resolving power, because here so it depends upon the two factors, basically the n, that is the refractive index, and mu, that is the angle. So mu is this angle, and refractive index is the medium. So suppose it is a dry microscope, then in that case we are using air. So refractive index of air will be considered, and the wet or oil immersion or water immersion. In that case, we have to take the n with respect to the our medium. So, and also the mu, it varies. So if it is, suppose if I put n as 1, or air, for air, then if I am changing the mu, then the numerical aperture will change. So if it is 7 degree, the working distance, so in that case the working distance will increase, and the numerical aperture will be 0.12. And if I reduce the working distance, then I'll be getting a better NA. So if I put the angle as 60 degree, then the numerical aperture will be 0.87. So because this is higher, so that's why we will be getting a better resolution. So that's why we try to get a we try to always select a higher mu angle. So the working distance of very high magnification of lenses, so around, that is around 100x or something. So in that case, the working distance will reduce. So from 10x to 100x, the working distance will reduce. But still, we can make use of a small angle also, if depending upon our sample or application. So there are this large working distance numerical objective also comes. So that is, but that will not give us better resolution. But in some cases, if we are, suppose if we are using a biological sample in which we have to keep our sample in a petri dish. So in that case, we cannot use a very small working distance. So in that case, we have to use these kind of objectives. So that was about the numerical aperture. And then so depending upon which medium we are using, so if I am using oil, so then I'll be keeping n as 1.5. So then I'll be getting maximum Na of around 1.4. And if I am using water immersion, then the refractive index is 1.33. In that case, I'll be getting a maximum numerical aperture of 1.2. So this is the wet immersion objectives. So then there are formula for the lateral resolution and the axial resolution. So the lateral resolution is the image generated when the two structures lying side by side are perpendicular to the beam. So suppose the lateral is the resolution in the x and y direction. So suppose this is our sample. So here the resolution of these lines will be called as the lateral resolution. And in the axial one, the ability to see the two structures that are side by side as separate and distinct when parallel to the beam. So suppose uh, there are stacked patterns in the z direction. So in that case, if we are able to stack the image in the z direction, so that will give us the axial resolution. That is the resolution in the z axis. So that is because of the higher frequency and short pulse length, which will provide us a better axial image, because it is depending upon the lambda. Again, both of them are depending upon the lambda, and there is a limit also. So beyond the lambda by 2 limit, we cannot able to resolve our material or object. So in that case, we have to take care of the of this limit, and because of this limit, we are moving towards the lower wavelength sources like X-rays or electrons. Then there are bright field and dark field images. So the most common sources of image contrast are particle mass and crystallinity. So because of the mass, if it is heavier, then it will be giving better contrast and crystallinity also. And then so heavier atoms scatter electrons more intensely than lighter atoms. Hence, in bright field mode, the regions with heavier atoms are darker. So in the if as you can see here, so this is a structure, and of basically these are some fibers. So because of the density of fibers, it is appearing dark, and the uh, basically the area other than the fiber is because there is no material over here, so this space is appearing light. So that is why we are getting the contrast. So this is a bright field image. So the bright area that serves as a background for objects viewed in an microscope. Then we are having a dark field image. So in this case, what happens? The background becomes dark, and the object becomes light. So that is the dark field image. So both of them gives us information about the sample. So depending upon our application and our requirement, we choose the field. So whether we want it as bright field or dark field. Then there are some errors which are called spherical and chromatic aberration in lenses. So spherical aberration means if there is a discontinuity in this lens surface. So if this sphere is not properly polished or not grind properly, so in that case we will be getting focus at different regions. So that is called as spherical aberration. And the chromatic aberration is because of the wavelength of the light. So suppose the visible light is falling over this lens, and since the visible light is having different wavelengths, so different so the refraction will be different for the different colors of the or color or wavelength of the light. So in that case, we will be getting different focuses. So that is again a kind of error which is called as chromatic aberration. This is because of the color or wavelength of the light, and the spherical aberration is because of the spherical nature of the lens. So these are two of the errors which are which we generally have to uh, consider, and these are kind of drawback of using multiple lenses. So this is a disadvantage, but still so to avoid that, we therefore shift to another source, or the electron microscopy that gives us better resolution, because of the because uh, it will not so in this case, since I have told about the lambda by 2 error, it is not an error, it is a limitation. So because of that limitation, we are switching towards the electron microscope, and in that also we do not get any this spherical or chromatic aberration. So that is the advantage of electron microscope. Then the critical illumination. So critical illumination is a method of specimen illumination used for transmitted and reflected light based optical microscope. So here we are using so here this is a source, and we are using a condenser and an objective and again an eyepiece. So multiple lenses are present here. So this is called as the uh, critical illumination. So this has the problem that evenness of illumination as an image of the illumination source is visible in the resulting image. And the polar illumination has largely replaced critical illumination in modern scientific light microscopy. Although it requires additional optics, but still it will be better. It will be less expensive, and therefore we have replaced the polar illumination in the with the the critical illumination with the polar illumination. So the polar illumination is the process that provides optimum contrast and resolution by focusing and countering the light path and spreading it evenly over the field of view. So here, as you can see, we have a aperture iris and field iris. So and the objective. So here, this is the light source, and the light is passing over it or from the lenses. So first it will pass through the image plane, then the iris or the pupil plane. So this is a basically uh, our how our eye works. So that is it is basically a correlation of our eye. So this is the and here is the sample. So that is how we are able to get the image. So this is another kind of illumination, that is the polar illumination. Then we have trans illumination. So in the trans illumination, we are using more number of lenses. So that is another problem. As I told, the more number of lenses we will be using, the more errors it will cause. So that is why. Uh, so there are other modes also, as I told. So that is why we switch to other microscopy techniques like atomic force microscopy, scanning tunneling microscopy, scanning electron microscopy, transmission electron microscopy, and X-ray microscopy. So, and other microscopy techniques also include scanning image microscopy, phase contrast microscope, scanning focal microscopy, confocal fluorescence microscopy, confocal reflectance microscopy, nonlinear microscopy, multiphoton microscopy, or differential interference contrast, that is DIC microscopy. So there are different microscopic techniques also are present. So the common difference between the spectroscopy and microscopy is that when so the microscopy is used when we want to visualize the object. So it will give us the visual representation of our object or material. However, in the spectroscopy, it will basically give us the idea about the structure or composition or the arrangement of the sample. So that is the basic difference between the microscopy and the spectroscopy. So now coming to the basics of optical microscopy. So the optical microscope is also called as light microscope. Is a type of microscope that commonly uses visible light and a system of lenses to generate magnified image of small object. So as I told, when we are using a visible light that contains different colors of light, and depending upon the object, so the object if it absorbs all the light, we see it as black because we are not able to get any reflected light out of it. So there will not be any color. And if it is absorbing a certain, if it is reflecting a certain kind of color, which is color of light or wavelength of light. So that is how we perceive it. So suppose here this green leaf is appearing green because it is reflecting the green color and absorbing all the other colors. So that is why we are seeing it as green. So similar phenomena happens in the optical microscope also. And these are the oldest microscopes. These are simple and mostly used, and it uses a visible wavelength of light. So as I told already, Leeuwenhoek was the first one who created the microscope and tried to zoom it at 270 times, and he started the research on the bacteria with the help of this optical microscope. So a simple microscope uses a lens and an eyepiece. So here we have. So this is a simple microscope which is having only one lens. So if we are putting the object at the middle, in between the uh, focal plane, so here if we are putting it between the focal volume, so will be getting a bigger image that will be virtual but magnified. So that is how the phenomena of my simple microscope works. So uh, this is a basically how we are able to see the bigger or magnified image of our object. Then we have compound microscope. So it will use more than two or more than two lenses. So it will try to multiply the magnification. So suppose if we are using only one lens, in that case we will be able to enhance the image height of image from here to here. So that will be very less. Or suppose it is uh, 2x times, two times of the original height. And if I will put one more lens, then the image will be multiplied. So the magnification will be multiplied. So from 2, I'll be getting 200x or 100x. So that is how it gets multiplied when we are using more number of lenses. So this is a schematic. That is how we are able to see our magnified image. So this is the image one. Then with the help of second lens, we are able to actually uh, get the bigger or magnified image of the object. So then the difference between the simple and compound microscope. So a simple microscope uses only one lens, and in the compound microscope we can use 3 to 5 lenses. Then condenser lens. So in the simple microscope we do not need any condenser lens. So it is absent in the simple microscope. But in the compound one we need to have a condenser lens also, and it is present in the compound microscope. So and the mirror type. So here we use concave reflecting, and in the compound microscope we use one side plane and other side concave. Then source of light natural. Here we use illuminator. Then the level of magnification. Here only one level only, but here we can multiply the magnification as I told already. Then the structure. So here we have a small stand is a small and hollow cylindrical attached to the base and is used to hold the microscope. And in the compound one, the arm is curved and it is used to hold the microscope. Then the uses. So the use of course, hooks and knobs is not too much, and the here the knobs are more, and it helps in focusing the image properly. So as a result, we will get a clear and concise image. Then so the usage. So here only one can only be used in simple ways because of the such as enlarging small letters or while reading, or also if we want to take a bigger picture of our material. So suppose we are seeing bacteria or cells. So if we want to see the bigger picture of how the bacteria are behaving or how the cells are behaving, so in that case, simple microscope can be used. But in the compound microscope, it will give a wide range of use. It can be used to study the structure of objects or details of the cells in the living organism. So depending upon that, so since here in the simple microscope, we will be getting magnification of up to 300 x, and in the compound one, we will be getting 2000 x. So that is the major difference. So if we want to see a bigger picture of our material, so in that case we will use a simple microscope. And if we want to see in depth what actually is happening or how the organism is behaving or the structure of the object, so in that case we will use a compound microscope. So again, another type of microscope is the confocal microscope. So here, what happens is that it is also called as a laser confocal scanning microscope, because scanning means we are not focused at the entire area, but we are because we are using a laser here. So only a small part of the region of interest will get eliminated illuminated, and with the help of a scanning or raster scan, we can actually at different parts of the region we are able to see the information. So suppose uh, it, it can move in a pattern like a serpentine pattern. So with that, we are able to make a image of our region of interest. So that is why it is called as scanning microscopy. And so here we have a laser which is passing through a filter. This is the excitation filter, and here we have a dichroic mirror. So it basically one part of it will be focused with the help of an objective. It will be focused on the specimen. And another important advantage of this confocal microscope is that in the even in the z direction we are able to focus it. So in the z direction also we are able to get the information. So suppose this is at the 0 nanometer that is on the surface. Then as we move down towards the surface, towards the center of the material. So suppose here 0 nanometer, then 10 nanometers, then 20 nanometers. So in the depth also we can get the information with the help of this microscope. So then from here it will again go back to the dichroic mirror. It will pass the emission emitted radiation. And again we have a filter here, so it will focus to the camera, and then we are able to get the image. So this is basically used for the dimension images or 3 dimension images, as I told, because in the z direction also we can get the information. And this is used for scientific and industrial communities and other applications in life sciences, semiconductor, or material sciences. So here the light travels to the sample under a conventional microscope as far into the specimen as it can penetrate. And while a confocal microscope only focuses a small beam of light at one narrow depth level at a time, and the laser scanning microscope achieves a controlled and highly limited depth of field. So here we can actually control our depth of field. So again the phase contrast microscopy. So here we use a aperture. This is the annulus aperture, which basically what it do it does the it changes the interference pattern. So here you can see there are slits, and then there are areas which are blocking the area. So that is because of this, as you can see here, this red one it will cause a destructive interference. In the yellow one where the light can pass, it will cause a constructive interference. So that is how we will be able to get a phase contrast. So there is a phase shift in the image, and it will what will happen that the unstained transparent object will be visible under the optical image. So the annulus aperture is placed in front focal plane of the condenser and limits the angle of penetrating light waves. So here the angle is changing basically, and uh, so a face plate is placed in the back focal plane of the object. Here, as you can see, the light waves which are not interacting with the specimen are focused as a bright red. So the background is seen as a bright color. So because this is not interfering with any objects, there is no object here. So that's why we are getting the background is white or bright, and the objects are becoming darker. So that is the basically phase contrast. So here there is no phase contrast or phase shift, and here we are getting positive phase shift. So again the changes is depending upon lambda by 4, and it dims the light. So that's why here we can see darker object, and the scattered light is shifted by minus lambda by 4. So that is why the contrast is happening. So the phase shift in scattered light is caused by the difference in the optical path length in the specimen, as you can see here. And because of the optical path length difference, the destructive and constructive interference are forming. Then we have fluorescence microscope or fluorescence imaging. So this uses the fluorescence and phosphorescence phenomena of the biochemical compound as a contrast mechanism. So here why we are seeing different colors, because as I told about the fluorescence phenomena, what happens when we are putting a suppose a UV light on this sample. So different depending upon its absorbance and emission property, it will emit different colors. So here I have to put a filter. So if I put a filter uh, which will not give me the red color. So in that case, I'll be getting the color of the image as something else other than the red. So that is how we'll be able to get a fluorescent image. So here you can see three different colors are there. RGB basically. So there are only three color we are able. That is the primary color, and the other colors are combination of those primary colors. So here, as you can see, three colors are there: the red one, and green and blue. That is the primary, and the other orangish color or something like that are because of the interference of the primary colors. So what is the importance of the fluorescence imaging is that we can stain different parts of a tissue with different dyes, and that is how we can visualize which part is what, and how it is behaving with our treatment. Or suppose these are, so normally, if I give a very basic example, so if I want to treat cancer cells with suppose I have developed a new drug, and if I want to see how that drug is killing, if it is killing the cancer cells or not, so that behavior I can see using the staining of these cells. So I stain the different parts of a cell. So suppose the nucleus is generally stained blue, and the other part is stained either green or red, depending upon the what organelle I'm focusing on. So either the Golgi complex or mitochondria or whatever part I want to observe. So suppose I have stained the mitochondria green and the nucleus blue. So that and then I do the fluorescence imaging of that. And so there is a one sample which is not treated with a drug, and then I can compare it with the one which is treated with the drug. So how the cells are behaving, if those are died or not, or how if they are disrupted or not. So that information I can get from the fluorescence imaging, because I'll be able to clearly differentiate the mitochondrial region or the membrane, cell membrane. So that information I can get from the fluorescence imaging. So that's why this is very important for a biological study. So then, so what are the different parts of the optical microscope? Let's look at that. So we have a eyepiece lens. So here is the eyepiece lens, which is used to look at the object, and then we have the tube which connects the eyepiece to the objective lens, and then we have objective lenses here. With this can be this turret is basically holds the objective lens. So these objectives can be of different magnification powers. Suppose 4x, 10x, 40x, 60x, even 100x. So there are different objective types. Then we have red stop. This is the adjustment that determines how close the objective lens can get to the side. So then we have a condenser lens. This is the purpose of the condenser lens is that it will focus the light in onto the specimen. So that is one of the components. Then we have a stage. There is a platform where we keep our sample or slides. Then the revolving mouthpiece turret. So this revolves basically, and we can switch to different between the different objectives. Then the illuminator or the source. So normally the source of 110 volts is used generally, and is in a place of a mirror. If your microscope has a mirror, it is used to reflect light from an external light source. And then we have an arm that supports the tube and external light source. And there is a base. So this is the bottom of the microscope. So the different parameters I have already mentioned. So one is the flat field correction and aberration correction. So plane means the objective is corrected for having a field curvature. Uh, so there are different characteristics which based on which we can actually get to know about the information on the objective lens. So what is the aberration correction? What is the flat field correction? Then the lateral magnification, that is the 68. So that means that it will enlarge 60 times with the magnification of 1x. Then we have the numerical aperture as I already told, so it depends upon the refractive index and the angles. Then, so this angle is the half angle of the maximum cone of light hit by the lens. Then we have the optical properties, different optical properties are there. And then the cover glass thickness, how much is the work, depending upon the working distance, basically we can specify the cover glass thickness. That is also one of the parameters of the objective lens. And then the working distance, obviously. So here as you can see, so this is the plane, plane means the flat field correction. Then APO means the aberration correction. And so here this is the company name or make name. And here is the this threaded part is the mounting thread, mostly is mounting thread. Then we have a lateral magnification that is 60x and numerical aperture mentioned over here. Then DIC, that is the specialized optical property, and here this gives the WD is the working distance, as shown here 0.15. And so this is the tube length, so we can use the tube length as per our requirement. And cover glass thickness range is mentioned here. Then cover glass adjustment gauge is mentioned here. This is the magnification color code. So if I want to see this, I want to know uh, the 60x objective, which one is it? If and I am not able to see the this uh, this text. So with the color on with the color of the objective, I will be able to identify which one is what. So this is particularly uh, universal for so suppose if it is 60x, it will be blue in color. So that is how I'll be knowing that okay, this is 60x by looking on the on this ring. Then we have the correction collar, and this is the front lens assembly element. So then we have different illumination techniques, as I already told you, bright field illumination. So this is by absorbing of the light on the sample, and the dark field illumination is because of the scattering of the light by the sample. So this is the major difference between the dark field image and the bright field image. Then we have for phase contrast, which will be because of the interference of the path length of light from the sample. Then we have cross polarized light illumination. This will because of the rotation of polarized light through the sample. So that is how will be able to get different illumination of the object. Then the application of my optical microscopy. So some of the application I have already told you, and it is also so for basically for metallurgical samples, we are able to see the grain boundaries in the optical microscope, then phase boundaries also. So different because of the crystallinity of the sample, the contrast will be different. So suppose there is a so this is suppose a steel sample which is having different kind of microstructures. So some is one is the ferrite and another is the martensite or austenite. So because of the different crystallinity, it is appearing different in color. So that is how I know that the material is having multiple phases. So that is one of the example. Then the microstructures. So in the metallurgy also we are able to use this optical microscope extensively. So then so the advantages and disadvantages, some of them I already told you. I'll again repeat. So the optical microscope can enlarge up to only 1,000 times mostly if I want to use multiple lenses. Then still the limit is only up to 1,000 times. Not because of more than that, because we are using light as a source. So lambda by 2 is the condition, and so that is a limitation. And so and because of that, the smaller detail is the 250 nanometer. Beyond that, we are not able to observe from the optical microscope. And the lightweight air is an acceptable thing. So for the living samples or biological samples, the optical microscope is a very good source for that, for the information on the living cells or bacteria or biological cells. Then in structure analysis, because of the light reflection, we are able to distinguish the basic phases or grain boundaries, or those kind of things can be distinguished because of the light reflection. So we'll be able to get color contrast in that. So again, these are the bright field and dark field images. So what is the technique basically? Here we are, so first one is the bright field. Here the transmitted light is actually seen here, as you can see. The light, this is a simple one, so light is focusing on the specimen with the help of an objective, and here we have a condenser, and that we are focusing it in the center. And in the dark field, what happens that on the object we are getting in the dark spot. So that means the light is getting diverted from the object. So that is why we are getting it. We are not getting any reflection from it, but the background will appear light. Uh, so the background will appear darker. That's why. And then we have reflected light bright field. So here we are not using a condenser lens. So this is the observed, this is the illuminated light path, and this is the observed light path. So one, this is the incident ray, it is falling on the sample, and from the same objective we are getting the reflected ray also. So the information is coming from the same source or same objective. So here the objective is acting as a condenser in the bright field also, and in the dark field it is it looks like this. Here also the condenser and objective are the same thing, but here the incident light is coming from this point, this path, and the reflected one is going from this. So that is the difference basically on the if it is transmitted type. So here we have objective and condenser both. If it is a reflected type, we have a objective which is equal to the condenser. That means only have one objective, one lens here, and depending upon our requirement, we have bright field and dark field arrangements. Then again, the basic difference I already told you, so I'll be skipping this part. So suppose if we are not using a light as a source, so what can be other possibilities? So as I told, we can use other radiations from the electromagnetic spectrum, example X-rays or electrons, etc. Or one more thing is that we can use a probe basically, like as as a to feel the surface basically. So in this case, we are imaging it by feeling the surface, like how it appears. So suppose we are not able to see the material, but we can touch it and feel it, like a blind person generally do. So he or she is trying to observe the surface by only touching the surface. So that is how here the scanning probe microscopy also works. That is the principle. And there are two techniques: the atomic force microscopy or the and the scanning tunneling microscopy. So in this atomic force microscopy, we use a cantilever beam which is having a tip, small tip attached to it, and the tip is interacting with the surface of the of our sample. And because of this forces, here it can be attractive force or repulsive force. Because of that, we are getting a signal from this cantilever, because it is bending towards the sample or away from the sample, and from that information we are able to see like what how is the surface or how is the roughness of our sample. Then in the scanning tunneling microscope, what happens that we have a metal tip over here and the sample, and one more thing, here the sample should be conductive because the electron charge transfer takes place. So as you can see here, so when the tip comes very close to this sample, it will try to uh, flow the electron. So electron will start flowing from there, like it will jump from the tip to the sample. So this is the tunneling process. So that is why it is called as scanning tunneling microscope. So here the electron transfer, this change we will observe, and here the force, repulsive or attractive force, this we will observe. And that is how we can produce the micrograph. So the history, so it was first developed by Gerd Binning and Heinrich Rohrer in the early 1980s at IBM Research, and later it was developed from the same person Binning and some more collaborators like Quart and Gerber in 1986 to further develop it, and then it was commercially available. And so the AFM is one of the foremost tools for measuring and manipulating matter at the nanoscale. So in the AFM, we will be getting a broad range of magnification from thousands of nanoscales to thousands of nanometers to few nanometers. So that is the advantage of AFM. So what is scanning tunneling microscope? So first, it uses the concept of quantum tunneling. So what is quantum tunneling? Quantum tunneling is a barrier penetration or simply tunneling of a electron from the because of the potential energy barrier. So here, as I told, it is so the sample and the tip are connected, and the voltage is applied, and when it reaches to a close area or nearby to the sample, it will try to the electron will try to jump from the tip to the sample. So that is how we know that there is something at the in the periphery or in the periphery of the tip. So that is how we know that the sample is here. And so when we scan the whole region, we know that how is our surface. So this is the schematic of a STM. So we have a probe here. So this is a piezoelectric probe with electrodes, and it is connected with the voltage. And then here we have a sample. So suppose the sample is stepped like this. So if it goes like linearly, it will damage the tip. So in that case, we have two things. First one is the if we keep the height as constant. So the difference, if it reaches near, it will try to again adjust itself because of the feedback loop. And again, the so suppose I kept the height as 10 nanometers, so it will adjust the height when it comes closer to the sample, and then we will be able to get the information. So like this, we will be able to get the information. And one more thing is the current. So if the current value, if I keep it constant, so in that case also it will not damage the tip, and scan it will give the information about the surface. So the principle is that two modes are there: current mode and the height mode, as I already told you. So depending upon these two, like we will be able to get the signal out of it. So if I put the current constant, so the height it will adjust automatically, and if I keep the height constant, the current I will get will be the will be my the processed or the information which is of the surface. So this is the basic principle of the STM. Then we have the AFM. So AFM is a category of the scanning probe microscopy, and it uses a raster scanning technique. So here we can get the information about the local height, friction, electronic and magnetic properties, and construct a map of this data to form an image. So again here also the scanning of the raster scan will happen of the region of interest, and it can be either 10 nanometers or 14 nanometers or even 40 micrometers also. So that area we can actually select how much we want to scan. So if we want to get a bigger picture, we can scan a 90 cross 90 or 100 cross 100 micrometers of the area. And if we want to see a very small area, or like molecule, so in that case, I'll be only focusing on 10 nanometers to 10 nanometers area. So that is the advantage of a AFM microscopy. So here we have a cantilever with a tip attached, and it is having, so the cantilever is having a reflective surface, so that when the laser falls over it, it will reflect back to the mirror. And here is a photodiode, which is basically a quadrant. Here, yeah, here it is the picture of the photodiode. Here, so what happens if this is diverted or deviated on any of the quadrant, so the feedback loop will try to get it back to the center. So that is the working of the that is how the feedback loop works for this instrument. So here, when the tip comes in contact with the sample, it will deviate. So the cantilever beam, it will deviate, and because of that, we'll get the information from the photodiode that how much it is deviating, and that deviation we can actually observe, and it will because of the feedback loop, it will come back again, and the piezoelectric scanner will help us to position our sample in the XYZ direction. And so this is about the instrumentation, and then we have a computer which controls the like different parameters, and the data acquisition and display. This will happen with the help of a computer. So what are the uh, different components? We have a prop tip, which is basically which is this is very hard tip, and it's the material is generally silicon nitride, and other things also can be used. Then we have a cantilever and a source, laser source. So here we have a laser source or diode, and then the sample stage. So sample can be moved, and piezoelectric scanner. This is the scanner which is attached to the sample, uh, not sample but the stage. And then we have a position sensitive photodiode. So this is the photodiode and the feedback control loop and a computer which displays the results. So the three modes are there for the imaging in the AFM. First one is the contact mode. So here it basically runs like this. Then it will come in contact with this and then goes like this. So in this case, there are high chances of damage to the tip, and the tip armstrongs from surface, this will get repelled, and there will be constant force overall on the on our sample, and it will give a highest resolution, but it can damage the surface also. And here high chances are there to damage the tip also if the sample is very hard or sticky. In that case, it will damage the tip. So we generally prefer non-contact and tapping mode. So in the non-contact mode, this is hundreds of armstrongs from surface, so it is attracted. So this will try to bend the cantilever. So it goes like this and then this like this. So here the force will be variable and it is measured, and so basically the attraction and repulsion forces are measured, and it has low resolution because it is not coming in contact with the sample, so we are not able to get a better resolution as compared to the contact mode, and it is non-destructive. So here we are not destructing the sample because we are not touching the tip with the sample, so this is non-destructive. Then we have tapping mode. So this is intermittent tip contact. It is again variable force method. So what happens that it goes to the sample, it touches the sample and come back, then again goes move like this and then goes and come back and then move like this. So like this, it is tapping on the surface of our sample. So it is non-destructive type, and it will also give a better improved resolution as compared to the non-contact. So the principle is that so basically we are measuring the forces which are acting between a fine tip and a sample. So the repulsive and attractive forces are what we are measuring. So the tip is attached to the free end of a spring cantilever. So this cantilever is attached to the spring, and therefore it is moving up and down, and like depending upon the forces, attractive and repulsive forces. It is brought very close to the surface. When the tip is brought within the interatomic separation between the tip and sample, the interatomic potential are developed, and because of that, the atoms of the tip and the atoms of the surface, resulting in an attractive or repulsive forces. So here, so depending upon the force, so repulsive forces and these are considered positive, and attractive forces are considered negative. So, in the contact mode, generally the repulsive forces, this area was is taken into consideration. In the non-contact mode, this area is taken into consideration, the attraction force type side. And in the tapping mode, again the equilibrium part, this area, this region is considered again the attraction side. So, and the force can be calculated using the Hooke's law, that is F is equals to minus kx. So, k is the spring constant of the cantilever, and x is the deflection because of the force of attraction. So, from this information, we can get the force, how much force is coming from the sample. And then this force is then converted into uh, the matrix, force matrix, and because and with the help of that we can get the micrograph. So here, so this is the principle, and we have four quadrants in the photodiode, and if it is deflecting, so if A plus B, it is going upside, that is a normal force. If it is coming down, that means C plus D. So this is the basically it will give the information to the closed loop, and then it will try to come back at the center position. So that is how we know that if it is going upward, that means if it is going in this region, that is upward. If it is going in the this region, that is downward. So we know the topography, basically how it is moving up or down, and the lateral force, left or right. So if it is going to the A plus C side, that means left. If it is going towards B plus D side, that means right. So the lateral force and normal force we will be able to get, and also the topography of the surface is also we can observe. So this is one of the example of the AFM image. So as you can see in the figure A, we are not able to observe any. This is just a 2D image. We are not able to see the heights, etc. And the B plot shows the height. So how it is varying in a particular plane. So if I put a line over here, I'll be getting this kind of topology plot. So this shows the height of of my sample. Then we have the 3D image. So this 3D image also we can get from the AFM. So here I just added the third dimension, Z stacking here, and like the Z image, and I know that the from the contrast gradient I know which how much is the height, so maximum height and minimum height I can observe using this 3D plot. And then we also get the information about the surface roughness also. So from the results we can get this kind of table, and we know that how much is the area which we have scanned, and the Rmax value and RQ value. So these are the information which we can get from the AFM. And for the AFM, like as I told already, so we can scan up from around 100 mm to 1 nanometer. So basically, this is the wide range of microscopy we can perform with the help of AFM. So the certain applications of AFM are mentioned here. So it is mostly commonly used for imaging surface topography by recording the position of a sample relative to the tip, and then recording the height of the probe that corresponds to a constant probe sample interaction, as well as the variety of mechanical, functional, and electrical properties. So it will give us the information about the height of the sample, or the sample roughness, and then we can also get the properties like mechanical properties or electrical properties based on the interaction of the probe and the sample. So if I have a piezoelectric material, so if it is deflecting upon interacting with the force, with the probe, that also I can observe using AFM. And there are certain other properties like other mechanical properties. What is the stiffness of the material, or this hardness of the material? That also I can observe using the AFM. Then for surface manipulation using tip forces, for scanning probe lithography, we can use this kind of this AFM, because when I put the tip, suppose if I put the tip and apply a force, then the surface might get manipulated, or if there is some kind of phase change or crystallinity change, that kind of thing can happen. Then to measure the forces between the sample and the probe, that is the commonly used application. This is the common application. So here, as I already told you, the force between the sample and the probe as a form of force spectroscopy. This can be used to examine the physical and mechanical properties. So if the sample is giving more force, that means it is harder or stiffer, and if it is giving less force, that means it is softer. So based on that, we can check the physical and mechanical properties of the sample. Then there are, so SPM is altogether is a powerful imaging and measurement technique that has become critical to nanoscale research and to industrial R&D, and it can be used for semiconductor science and technology, thin film and coating, tribology also. So for the sample topography and friction interaction that we can observe. Surface chemistry we can observe. Polymer chemistry and physics. Then cell biology, molecular biology, energy storage also, and energy generation, photovoltaic materials, etc. we can observe. And the piezoelectric and ferroelectric materials, as I already told you, it can also be checked in the using the SPM. So the difference between AFM and STM. So in the STM, the resolution of STM is better than the AFM, because in AFM we will not be able to get a proper like more resolution, but in STM, because of the electron transfer, we'll be able to get very sensitive information. So that will be very sensitive as compared to the AFM. So that's why we'll be getting a better resolution in STM. And STM is applicable to only conducting samples, so only for metals it is used. And but the AFM is applicable for both conductors and insulators. So this is one of the advantage of AFM, that it can be used for conducting samples as well as insulating samples. Then, so difference between the AFM and optical microscopy. So AFM provides more information and far higher resolution than optical microscopy, as I already told you. And compared to the optical microscopy, AFM overcomes the wavelength limitation, that is the lambda by 2 limitation, because we are not using any visible light here for acquiring the data, but we are using the probe technique over here, and this is capable to acquire 3 dimensional tomography also, and molecular interaction and dynamics under various conditions. So even in vacuum we can use it, or atmosphere, and also in the liquid medium we can use this. And also we are able to conduct this in atmosphere, so this is the advantage over the electron microscopy, that in the AFM and optical microscopy we are able to use the material in the atmosphere, or use see the sample in the atmosphere. So that is very helpful when we are doing the molecular biology or any kind of microbiology studies. So there are different scanning probe microscopy. For example, I talked about the scanning tunneling microscopy and the AFM, and then we have Kelvin probe force microscopy, then electrostatic force microscopy, photoconductive AFM, then conductive AFM, then friction force microscopy, spectroscopy, piezo response force microscopy. These are all can be done using a probe. Basically these are types of AFM only. So here we are using different types of interaction. So basically we have the electrostatic interaction. If we are checking, then this that becomes the electrostatic FM. Then photoconductive property, if we are checking, depending upon the source, if we are putting a source over here, and then we see the conductivity, that is another type, that is photoconductive atomic force microscopy. And then if the sample is conductive, then conductive atomic force microscopy. Then if we are checking the friction force, and friction force microscopy it is called. Then the force spectroscopy also, that is another type. Then piezo response. So if I want to check the piezo response of a material, of a piezoelectric material or something like that, then I can use this microscopy. Then I already talked about the scanning, tunneling, spectroscopy and microscopy. Those two can be also called as scanning probe microscopy. So these are multiple types of SPMs which are commonly present. So now coming to the questions. So a polarized light is unidirectional, bidirectional, multidirectional, or none of them. So can you able to answer this? Any of you? Yeah, exactly. So because we put a polarizer over here over the unpolarized light to get a unidirectional light. So that is called as a polarized light. So the answer A is correct one. Then the second one is which one of the following statement is incorrect? Secondary electron imaging correspond to topography. Energy dispersive X-ray spectroscopy provides data about phase difference. Inelastic scattering leads to secondary electron emission. Elastic scattering leads to backscattering electrons. Actually, I have not included the scanning SEM one, the electron microscopy, because because of the time constraints. But I think you have learned about this in the modules, so I hope you can answer this. In the previous session, also, I tried to explain the interaction of the electron with the matter. So, depending upon that, also you can try to answer this question. So, which one should be the correct answer, or which statement is incorrect, basically? Can anyone explain? Guess? Or, yeah, exactly. Okay, but the answer is B because this EDS will not give us the information about the phase difference. So the other all three are correct one. So I can draw it. So suppose this is our surface of the our sample, and the electron beam is falling on it. So the secondary electron basically are those from the surface. So this will give us the information from the topography, that means the surface. Then there is inelastic scattering, inelastic scattering, and the elastic scattering. So elastic scattering means the back scatter. Sorry, not this direction. So if the angle is very less, this is the back scattered electron. So here the elastic scattering means there is no loss in the information, loss in the energy. So that is the best back scattered electrons. And if there is a loss in energy, that is called inelastic scattering. That leads to the secondary emission, as I already told you. So this one is the secondary electron. This is because of the inelastic collision or inelastic scattering, and this is the back scattered, which will be the angle between these two, incident one and the back scattered one, is less, and it is elastic scattering, and that gives us the information on the bulk, and the secondary one will give us the information on the topography. And this energy dispersive X-rays are the ones which are characteristic X-rays that gives the elemental composition, but it will not give us the data on the phase difference. So that is the correct step. I hope you understood. Like if you have doubts, you can ask. Is it clear? Okay. Yeah. Yes. 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 Okay. So yeah. So basically, when the when the beam is interacting with the matter, so if it is going in depth, it will interfere with the matter, right? It will interact with the matter. And in those cases, so here as you can see, for the secondary electron emission, the angle is large. That means it is highly scattered. So if it is scattering is nothing but the deviation of light basically. So if it is scattering a lot, that means it is interacting with so many objects in between. So suppose in its path, a lot of obstacles are coming. You can consider it like that. And because of those obstacles, like those obstacles can be atoms, it can be atoms or any like molecules or something. So that are absorbing the light, and because of that, the intensity reduces. So that is why we are getting inelastic scattering. That means the intensity will be lesser. Means the energy will be lesser because the molecules or atoms are absorbing the radiation or light. So because of that, we are getting inelastic collision here. And the elastic one means there is no change in the there is no change in the energy. So that is how we can differentiate. I hope I answered your question. So the next one is the choose the correct option. So there are three regions A, B, and C, and which one corresponds to which mode in the AFM. So can you tell me, like I just discussed this diagram in my previous slides. So the first one is mainly considering the repulsive forces. Then the second one is considering the attraction force, and the C one is the C region is considering the attraction force at the equilibrium region. So depending upon these forces, can you uh, differentiate the contact modes, so contact type or tapping type or non-contact type? So what should be the answer for this? Like I just now explained this. Any guesses? Like B or D? Yeah, D is the correct option. Because in the so A region is the contact mode type because we are trying to observe the repulsive forces. Then B, this region is the non-contact type, and the C region is the tapping mode type. So option B is the correct. Then choose the increasing order of resolution from the following. So optical, AFM, TEM, and HRTM, like and SEM also we are having. So what will be the resolution order for these techniques? Although I have not explained the electron microscopy technique, but I'll just tell you that electron microscope will be having higher resolution, obviously because of the lambda by 2 limit is not there in the electron microscopy, and that is one of the hint I have given you. So depending upon that, like which one is the correct answer? Any guesses? No. Okay, so option A is the correct one. So I'll explain how. So first one is the optical one, which is having least resolution because of the limit of lambda by 2. Then we have AFM. So AFM will be having higher resolution than optical, but lesser than the electron one. So uh, because in this we will be able to see from around 10 nanometers or so in the AFM. Then in the TEM, it is even higher resolution, and the HRTM is anyone of you know the HR. What is the full form of HRTM? Yeah, exactly. Yeah, so the name only tells that it is high resolution TEM. So it basically gives the idea about the structure of atoms or how the arrangement of atoms. So that goes up to Armstrong levels. So that's why it is very high order of resolution. So the correct order is the option A. So we can see why the other options are wrong. So here HRTM is having lesser resolution than AFM, that is the wrong statement. Then here we are having AFM more resolution than the SEM, that is again wrong, because electron microscopy will be having more resolution. And in the third one, the first two are same, but here the HR1 is having less resolution than TEM, that is also wrong statement. So the option A is correct. Now this question, we have to match the following. So there are different techniques which is having uh, like related terms. So which one is related to what is what we have to like match. So any guesses? Yeah, C or D. Okay, let's see. Yeah. Okay. Yeah. It, uh, so D is the correct one. Yeah, so the electropolishing, it is related to the metals. In the metals only we can polish the sample or deposit other element using the electro deposition or technique or electropolishing also. Then ultramicrotomy, that is used for polymers or biological samples. Then FESEM means, so this is a misprint. It is FESEM, and Fe means the field emission. So here why Fe? Because we use field emission gun as a source of electron. So that is the correct match for third one. And scanning probe is a STM technique. So scanning probe is a broader uh, view of the STM. So STM comes under scanning probe. So option D is the correct. So I'll be discussing the electron microscopy later because we have time constraint. So if you have any questions, you can ask me. And I think Bhupati, you were not present in the you were not in the earlier when I when you I think you joined late. So and you asked me the question about the UPS. So I explained it in the when I started the lecture. So you can go through the recording, or you can I can give a brief overview also if you want me to. So, oh, so any questions? The pro. Uh, mm, okay. Yeah. Okay. So de Broglie equation. Yeah. Yeah. I understand. So de Broglie equation is lambda. Okay. So I'll just write it down. Lambda equals h by m nu. So this is the equation. So what is your question basically? So you have to solve the numerical, right? Yeah, you can tell me the question. Yeah. Okay. Yeah, so mass you have, and v here is the velocity of light. Yes, velocity. So these two you have, and h is the Planck's constant, right? So from here you can calculate the de Broglie wavelength, I guess. Yeah, h is the Planck's constant. Right. Yeah, 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 exactly. Joule. So yeah, minus 34. Yeah. So m is the mass. This is in kg. Planck's constant. This will be joule per hertz. Yeah, yeah, you can solve. Okay, okay. Make sure you are here the units are same as like when you are keeping the putting the values, the unit should be like this. Okay, and mass should be in kg, velocity in meters per second, and Planck's constant joule per. Yeah. So actually the Planck's constant this 6.62, this is in joule second. So you have to convert it into hertz. Yeah. So it should be in frequency. That means 1 by. I think it is same only, right? If you put joule, yeah, 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 yeah. It is. It's second only. Yeah, that is correct. No, no, that is. I think it is same. Yeah, and it should be 6.26. So you are not getting the answer with this. Yeah. So you are getting the answer, right? Or should I solve it like? Then yeah, yeah, that is simple. Okay, so for that one, you have to use this formula. F is equals to minus kx. Yeah. So what what was the problem? what problem we are facing. Okay. So now you have to convert this. Yeah. So you have to convert this into meter. Did you do that? Yeah. So I think this is a simple, straightforward question. So if I put it here, yeah. So what are the options? So what are the options? Can you tell the option? 5 is the correct. Yeah, 5 into 10 to the power minus 9 should be the answer. I think there is some error in the question itself. So okay, this one, the de Broglie one. Can you okay? Can you tell me the mass in this problem? What was the mass and velocity? Okay, kg. Yeah, that is. Okay, I'll try to solve it. Just so what are the options? Okay, so it's on meters. It's in meters. Okay. Uh, I have to check. Just a second. I think my answer is yeah. So my answer is coming closer to the option C. That is 0.25 into 10 to the power. I'm getting 10 to the power minus 5. Uh, but I'm not sure if 5, yes. Yeah. No, okay, wait. Just 8, 11 I'm getting. Hello? Hello? Can you repeat the options? Yeah, okay. No, no, wait, I'll stop everything, then you can share. Is it coming 57? 10 to the power minus 57 or something like that? Hello? Okay, yeah, 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 uh, yeah, I understood. So I'm trying to again solve it. Yeah, I'll write it. I'm writing in the chat box. Yeah, yeah. Actually, from the de Broglie equation, it is h by mv, so it should be straightforward. But there might be some error in the question, in the options that can be possible. But let's see. I'll try to solve it one more time, and if I get successful, then I will share with you. So you can, yeah. So you can mail me the query. I will look at it. Yeah. Okay. Okay. So any other doubt or questions? If okay. So if no more questions, then we can conclude this session. Thank you all for joining.